In this video, we're going to be analyzing a situation where we're going to be finding temperatures before and after, the work, change in internal energy, and the heat. We're also going to be applying the first law of thermodynamics to find a couple of our solutions. So we have 1 mole of helium that's in a 10-liter container. So we have an initial volume over here of 10 liters, and then it's compressed to a volume of 3 liters. And it says solve for the following values if the pressure stays at 200,000 pascals. So the pressure is a constant 200,000 pascals, which means it's an isobaric situation where the pressure remains constant under both conditions. Now we also have 1 mole of helium. So that means N equals 1. And we have helium as our gas particle. All right, so let's go ahead and solve for our 2 temperatures. Now what we're going to have to use is we're going to have to go ahead and use PV equals nRT. And if I do a bit of rearranging, I can divide both sides by nR, and I can solve for my T values. With that being said, I have my pressure of 200,000 times my initial volume of 10 liters, and I'm going to go ahead and take that 10 liters and convert it into meters cubed. And once I divide that by 1,000, that's going to come out to 0.01 meters cubed. So there's my V, 0.01, and then divided by the number of moles, which is just 1, and my gas constant 8.314. And then that comes out to 240.56 Kelvin. Now, as for my second calculation, we would do something very similar. We would have all the same numbers, except for my T2. We would be swapping out a different volume. So the whole entire setup would look fairly similar. We would still have the same pressure, 200,000, except we would take 3 liters and divide that by 1,000, which would change it to 0.003. And then divide that by 1 mole and the gas constant of 8.314. And that leaves me with a temperature of 72.17 Kelvin. Now we went ahead and recorded our 2 T values up top here so we can keep a record of what we got for some of our solutions. And we're going to go ahead and solve for the amount of work done. Now, if we're solving for the amount of work done, if we're concentrating on the system, we're going to call it negative P times delta V. If you're focusing on the surroundings, you would drop the negative. Now we have work equal to the pressure. We know the pressure is 200,000 pascals. And we have a delta V. And remember, we did some conversions to change these, but it's always the final minus the initial. Now from there, we would take the negative times 200,000 pascals, go ahead and find the difference of these two, which would leave us with negative 0.007 meters cubed. And then when we find the product of those two things, that will leave us with a work value of 1,400 joules. And that would be positive because of the negative up front over here, multiplied by the negative over here. Now the work would be considered a positive value because the surroundings are applying a force over a distance and compressing this container down to 3 liters and then adding energy into the system. So we have 1,400 joules for our value of work. Now moving on, let's go ahead and find our delta U, the change in internal energy. Now, if we want to find U, that would be 3/2 on our T for a monoatomic gas. So just regular He helium is monoatomic. It's just that single atom on its own. Therefore, we're going to use 3/2 as our coefficient. And if we want a delta U, all we have to do is find a delta T. So we're going to do final minus initial temperature, which is basically our T2 minus our T1. So we have delta U equals 3/2 or 1.5 times 1 mole times our gas constant, and then our final temperature was 72.17 minus our initial temperature of 240.56. So we have a negative delta T, which would give us a negative delta U. Punch that in, and it comes out to about negative 2099.99 joules. Let's go ahead and log that in with our solutions over here, negative 2099.99 joules. All right, so we're ready to go into our final step, which is finding our Q value, the heat transfer. Now for this, we're going to go ahead and use the first law of thermodynamics and say that our delta U is equal to Q plus W, and it's Q plus W focusing on the system. It would be Q minus W focusing on the surroundings. So we're still focusing on our system, which is basically the gas inside the container there. So we have a delta U of negative 2099.99 joules on this side. We do not know the Q value, and we know the work value is 1,400 joules. So for this one, we would just do one step of algebra here. And then we would get a Q value of negative 3,499.99 joules, which means that the system is getting colder, as we already knew, from 240.56 Kelvin to 72.17. That was a significant amount of heat transferred out to the surroundings. So although work was being done on the surroundings or on the system by the surroundings, and it got that positive 1,400 joules, that wasn't quite enough to counteract the amount of heat that was being transferred out of the system. Therefore, the total energy ended up being a decently large negative value for our delta U. So I hope that was helpful in breaking down how to find the temperatures, work, delta U, and the Q. Thank you for watching and listening.